I'm going to give you a
Okay, so hi there. I'm here to talk about an anomaly catalog that we're building for the Dark Energy Survey. This is joint work with Eric Huff and Carrie Wagstaff, who are also at JPL. So I think everyone in this room knows that astronomy has a very long history of accidental discovery. So these are just three of examples of gamma ray bursts, fast radio bursts, and gravitational lens observations. And I thought I would include a slide that I saw at a talk last week. So this is courtesy of Jason Wright, who was giving a talk about technosignatures, which is sort of the ultimate anomaly detection problem of how are we going to find, how do we look through massive data sets looking for signatures of potentially advanced civilizations in our galaxy, maybe even outside of it. So I like this slide because it still essentially is what anomaly detection is supposed to be doing, at least a blind search through a catalog, right? So we have many, many examples of, normal or natural objects, and we want to examine sort of that middle layer between the upper limit where there are no sort of observable objects, and then the things in that middle layer are potential SETI candidates, extreme natural objects, so all the things that we consider interesting and may want to take a second look at. And that was our approach with the Dark Energy Survey. So we are kind of looking at that middle layer of sort of less frequent, sort of anomalous objects. There are a lot of potential astronomical anomalies. There are also a lot of data artifacts in there, and we want to mine it out. So the results I'm going to be showing here to you are actually results from a search on about a 12 million catalog of what's considered gold observations from the DES Year 3 catalog. This is after a lot of sort of suggested data quality cuts were applied. And so there are a lot of machine learning algorithms out there for anomaly detection, but I would argue that generally their output is not particularly useful because a single algorithm only outputs a ranked list of scores. So this is a plot of the anomaly scores coming out of the isolation forest. They're all normalized within a range of -5 to 0.5, where theoretically anything below 0 is anomalous. And if I want to look at all of the objects up until sort of that knee bend in the curve, well, that's about 50,000 examples, and that's often a 12 million catalog where you can imagine if you're looking at billions of objects, the space that you want to search is probably going to be millions large. So it's a very large amount of objects we want to look at. The implied framework of most anomaly detection methods is you prepare your data, you run some sort of algorithm, you review it, and you follow up and discard it. And what we're trying to do is expand that framework. So you still have the preparing your data, running the anomaly detection, but then you have to add a few sort of steps, which is to explain and contextualize your anomalies, and then to organize them, because if the space that you're looking at is hundreds of thousands large, we need a way to sort of be able to sift through them quickly, or in a more efficient way, I should say. And then when we review, we're not only reviewing, but we're also classifying, so we can be able to maybe do some more machine learning from that point. And then we move to our step where we either follow up, report to data pipeline people, or request follow-up time. So in terms of preparing data for our DES prototype, so as I said, we looked at a 10% subsample of DES Year 3 catalog of galaxy observations only, so that's about 12 million sources. So DES images in GRI and Z. We converted all the fluxes to leptitudes, and we looked at 4 features. So it's a very low dimensional space compared to what some of you might be typically operating in. But we're looking at sort of the R band and the G-R, I-R, and Z-R colors. So the next step, once you've prepared your data, is to run your anomaly detection. There are many, many anomaly detection methods to choose from. That's not really the focus of this talk. But we're looking for methods that are explainable, as the last session spoke to. There is a trade-off between the power of the model and the ease of its explanations, or its ability to explain. our prototype uses the isolation forest, which is readily available through sklearn, and also DMUD, which was developed at JPL specifically for explaining scientific data. And I'm just going to briefly talk about those algorithms. So the isolation forest works under the premise that outliers are easily isolated by random partitions of the data. So on the right side, you have an outlier which can be partitioned or isolated in about 4 partitions of the data, whereas on the on the left side, there is something that's a relative inlier that requires more partitions to isolate it into its own box. So we use it. It's a pretty fast method, computationally cheap. It's potentially, in future work, we're going to look at explaining it by drawing the hyperrectangles that encapsulate the given outlier as a sort of explanation framework for it. So DMUD is another outlier detection method that we use. It's the math underneath it uses singular value decomposition. So as a result, it's actually easy to reconstruct your original feature space from the principal components. And so the DMUD generates these plots, which are explanation plots, which gives you a sense of what it had expected this particular observation to look like versus, so that would be the red line, versus the actual observations that it saw. So any major sort of deviations or large residuals that you see constitute the explanation for why this, for why this example was chosen as anomalous. So once you run your anomaly detection, we have to explain and contextualize our anomalies for expert review. So we talked a little bit about explanations. I think everyone in this room would agree that explanations are increasingly important to the science consumers of these algorithms. I bring up the word context because we have to remember that these machine learning algorithms are operating on data stripped of their context. So it's helpful to kind of bring that back and look at the spatial, spectral, and even the temporal neighborhood that observation was made in order to better understand why this thing is anomalous. So we bring all of these components together in something we built. We call it a rapid labeling tool. So I'm going to go through each of the pieces. So this is what the tool shows you for one specific observation. And I'll step through each of them one at a time. So the first thing is obviously, if you're dealing with image data, is to look at the postage stamps around the source from the original image. So these are the postage stamps for the DES coads and all of the bands. And here's an RGB composite made from the ZI and R bands. And below that are the NG mix model fits. So I'm actually stepping through an example of what we believe is, I think, a transient that was found in the R band. So it actually has a relatively simple explanation, which is easy to show you. So you can see the transient in the R band, and that's why it shows up colored blue in the composite. There's the MGNIX model fit here is shown below. So this shows you how well the photometric modeling had worked. So there is, it might be hard for you guys to see on this screen, but there actually is a point source blob across all of the bands here. In terms of context, we also look at coincident imagery. So in this case, we look at, we're pulling WISE and GALAX data. The red box is showing you how that DES postage stamp that I showed you before fits inside this imagery. So WISE and GALAX have a much larger spatial resolution, or smaller spatial resolution. So this is used in the cases where there is sort of a real source that GALAX or WISE picks, and we can confirm whether there's something potentially astrophysical there. But it's something that we use to sort of verify and double check and see what other bands have seen at that location in the sky. So explanations can be algorithmic agnostic or algorithmic specific. So since we're in a very small feature space, we're actually able to pull up sort of pairwise plots and see where this particular observation, which would be a red dot on those 2D histograms, would show up. And so in this case, this particular transient is anomalous pretty much only in the R band. So it shows up as relatively normal in all the 3 colors, but it's anomalous just in the R band. If you look at the DMUD explanation, so this is an explanation generated by the DMUD algorithm, it also picked up that this observation was anomalous in the R band. So once you have a list of anomalies, which is each of these observations have a score attached to it, we want to organize the anomalies because a global rank ordering, as I mentioned before, isn't useful. Similar items might be ranked together or they might not be. As you can see, this is actually the plot of isolation, the first 100 outliers of the isolation forest plotted on these 2D contour plots. And you can see that there's some structure there, and we should be able to take advantage of clusters that exist and be able to present visually similar things or things that are similar in feature space back to the expert reviewer just for efficiency of review. So we're getting close to the final step, which is to review and classify the anomalies, and we developed 4 categories for classification for this particular task. So the first category is that you found what you think is potentially something scientifically interesting. The next one is that there are 2 kinds of artifacts you could find: some artifact of your data or the image, or some error of the modeling or measurement pipeline. And of course, it could be none of the above. And in this case, flagging the data artifacts is incredibly useful because DES is still refining their catalogs, and that feedback to them of, in your supposed gold cuts of your data, we're finding tons of data artifacts, is useful to them to help refine their threshold cuts. So just looking at some preliminary results, these are examples of data artifacts that were found in this gold catalog data. So supposedly gold catalog data. So there are a lot of examples of non-detections. There is actually a streak in the I band, a very faint streak in the I band, a very diffuse, I should say, faint streak in the I band that's present. That was flagged as a source, but there's no source present there. We also found another data artifact, which looks like some bad masking was applied. There are tons and tons of modeling errors. So this is an example of a case where there is a source present, but the model picked up flux from the adjacent sources and fit a much larger model fit to it than the actual source. And that actually threw off the photometric estimates and resulted in it becoming an outlier. So these are sort of basic things that we can feed back to the DES team and show them how their modeling is not working well. So this is an ongoing project, and these are some of the examples of outliers that were found that we have confirmed do seem to be astronomical sources. They are interesting for a variety of reasons. There are some blended sources here. There are extended sources. There are sources with unusual colors. It looks like we found, oh wow, this is really dark. But it looks like we found in the top right corner like an asteroid, which you can see kind of moving across the image in the different bands. So that's the next step, is we find the artifacts, but then we also want to look into the potentially interesting stuff and see if we want to submit a Palomar proposal or something along those lines. So in conclusion, this type of framework can be used to build catalogs of weirdos for any particular astronomical survey. So for now, we've applied it to DES data. Our goal is to also open source all the software tools in our framework so that people in the community could use it. We want to include other algorithmic specific explanations. As I mentioned, we're building something for the isolation forest. And we'll look at the field of explanations for machine learning algorithms is exploding. So the choice of algorithm doesn't matter so much as long as the ability to choose something that has some sort of post hoc explanation, or maybe something that's naturally interpretable. Eventually, we're going to expand this to the full DES data set. We also will be applying this to GalXWise and SDSS, and ideally explore synergies with SphereX and W first. So that's it. Thanks so much.